So what's going here? Couple things before we get into it. So I uploaded kind of this new multiple linear regression slides onto Canvas. So I took kind of where we left off last class, edited, got through in the week 5 slides and updated those. So these kind of contain some of the stuff we covered last week, but all of the multiple linear regression material. So what we kind of started on in Thursday's class, and then everything we'll do this week. Okay. So you still got those sample questions. After class on Thursday, I think we'll probably have gotten through enough material that I'll post that third quiz, right? So that'll be due a week Thursday. So you have a week to kind of get on. You can start reviewing it. We've covered a lot of the material even already. There's really only 1 or 2 questions, even while I'm not posting it today, that we probably won't cover until Thursday's class. So start reviewing those materials, kind of thinking about preparing for that quiz. I'll also be posting, I'm hoping to get it up tomorrow. If not, likely sometime on Thursday. 2 weeks from Thursday, first midterm month. So I'll get up a set of practice problems so you can kind of start thinking, or a practice exam, start thinking about preparing for that exam. And we'll be doing new material next week. But then I think we should have covered everything. But that Tuesday before the exam, so I think the date is the 16th, is that Thursday? That Tuesday, the 14th, we'll basically be just doing reviewing class. So that'll be a really good class to be at, because I will likely work through problems that might look similar to, well, I wrote the exam, so I kind of know what's on it. So I'm probably going to make the best use of that time. Okay. I'm getting a little concerned about the attendance in this class. We'll see. You guys are in the right place. So I'm not talking to you. Okay, people maybe watching these videos. The exam is going to be tough if you've kind of checked out and not been attending class and kind of seeing what we're doing in class. So keep showing up, making sure you're kind of staying up to date with class. So we'll kind of start multiple linear regression here today. One other things I wanted to mention before we get going. So I mentioned the quiz, that next problem set. There'll be one more problem set before the exam. So problem set 3, I'll get that posted tomorrow. You should be able to do everything except for the last problem on that problem set after today, or maybe the last 2 problems, but you can at least start taking a pretty good chunk out of it. You want to start working on it. So I graded the first problem set, and some things that I'm noticing. I'm guessing people are using Google and things for help with Stata. Anything I ask you to do, there is something in the do files we've used in class that does the exact same thing with different variables. So when you're making mistakes because you're trying to Google alternative ways that are actually more complicated, some of the things you're turning in, I know that I didn't teach you. You're looking at outside sources. Usually those are more errors on those. And that's probably because they're more difficult. I'm showing you how to do things that are a more simplistic way for a reason. Anything that you should have to do for those homeworks should be somewhere in the do files we're using in class. Okay. That problem set 2. So that is going to be due, where are we at? It's supposed to be due at the end of the day, Thursday. I'm going to extend it to be the end of the week. A couple of you have contacted me. There was an issue with Stata over the last 48 hours to 3 days, somewhere in there, where after talking with them yesterday and finally getting a hold of them this morning at 8 a.m., because that's the only time that I don't get put on hold. They had something on their end where there was an update in Stata, but you can't run the updates because it's not actually your program. And so it was preventing you from opening any files, not even, it wouldn't even give you the option, right? So that should be corrected. The 3 of you who contacted me, I've reached out to, and it's now working for. At least the 3 of you who emailed me about it. So if that was an issue, try to do it today, and that problem should be resolved. It was the same on my device, and it was resolved this morning after talking with them. So that should be kind of good to go now. But just in case there was a day lost where you were going to work on it, extend it another day, kind of the end of the day, Friday instead. Okay. But any files you had already saved, that nothing went away. It was just an issue with using the program from IU Anywhere. Did anyone have issues with it for the last couple of days? A handful. Yeah, so that for whatever reason, they didn't run the update over the weekend and basically didn't do it yesterday. And so it happened today. Okay. Any other questions for me before we jump into material here today? Yeah.
The new do and DTA file for week 5, is that different from, did you add anything to those files that weren't?
So when I updated, where are they at? I moved them to 6. So the MLR week 6, this will be the one that we're kind of using this week. The old one, I think, is still sitting in mod in week 4 because we used it for week 4 and 5. I think I cut out some of the end of it that was multiple linear regression. So it should just be simple linear regression stuff that we've already done. And then all the multiple linear regression stuff is just in that one do file. So I think if I updated it, it's because I wanted to make sure all the simple linear regression stuff was one do file, all the multiple was one. Since we kind of started last week, I had to have some of that material in the do file, but now I've got it. Does that make sense?
Yeah.
Yep.
Thank you.
Well, I think we talked about this before we turned in the first thing, but like I got my grade back and I was looking at the notes. So when they're being graded, if we get the right answer and we use code that like looks super good, do we get full credit? And then
So some of you had an issue with, first of all, if your code was incorrect, like it didn't work, you should have been able to get the correct answer. So what do I think you were probably doing? Working with someone else, doing it in another program. So you're graded for both having code that it's not one set way of doing it. There's several ways to answer the same question technically in some of the code. But if you have code that's not creating the correct answer, then you will lose points. So part of it is having correct code that will produce the answer. And the other half is generally when we're producing this code, it'll give us like an output. There's not just one statistic, right? And so you need to report what that actual statistic is. Or if you create a new variable, you need to know how to find that variable and find what that actual value you created is. So for every question, you should have a line of code that works correctly, produces the correct answer, and also identify what that correct answer is. And I can kind of point that out along the way today with some things we're doing about here's the code, but then what would be the follow-up answer to the question? That some of them you actually have to use some of the output and then do some like small calculations, right? Multiplying it by 10 or, you know, doing some like small amount of work outside of the. If you have questions specifically over your grade, we can talk about it either after class or during office hours would be a good time to kind of go through that. Does that answer your question?
I was just kind of like saying, because like for one of them, I use the keep command for conditionals. And I'm saying I got the answer wrong, but technically I should have gotten it right because I probably did something else wrong as well, like the numbers.
Yeah, we can work through it. So a problem sometimes using that keep command is it drops the data. So I think the issue on a couple that I graded, because I have my TA help, I think I mentioned before, grade half, and then I do the other half for the next problem set, but flip-flop. If you use that keep command, a lot of the times you'll drop the data, and then the next problem is where the issue actually arose, because now you're working with a data set that's not the full data set. And so then your answer to that question is going to be incorrect. So that's why it's kind of a coding error, because you shouldn't really be using that keep command unless you're keeping and then re-uploading, having a line where you upload those, that use the actual full set of data. But if you have an individual problem, we can kind of work through that. Okay. Any other questions before we kind of get going? All right. So. Well, hopefully. We talked about all of this last class. We were thinking about adding in multiple regressions. We had some of these examples, correlation versus causation. I then kind of showed you this omitted variable slide and said, okay, we run a very simple linear regression where I try to predict a y variable with one x variable. I'm not accounting for a lot of other factors, right? This is the idea. If I look at maternal smoking, it looks like it has a huge negative impact on birth weights or negative health on or impact on the baby's health. But there's a lot of other things correlated with that I'm not controlling for. So this is basically the proof of what that bias is going to exist in that simple linear regression if you ignore these other variables that are correlated with both the y and the x variable, and they're omitted from your regression. So we're not really going to ever take a look at that again because that math is kind of outside the scope of this class, and it's not ultimately that interesting. I mean, it's just a lot for us to do. We're applying the econometrics as opposed to just working brute force through the mathematics. So let's say I've got this regression where I've got two variables, x1, x2, and I think they both help me predict y, okay? If I run a simple linear regression and I leave out x2, and I know that it impacts both y and x1, okay? I will then have a slope coefficient beta 1 that is biased or incorrect. So the sign of that bias, sometimes we can't avoid this because we don't have data on this second variable. But what we can do is run our simple linear regression and say, I know that I have this really important omitted variable, and I can at least put a sign to the direction of my bias. Right? So in my maternal smoking one, even though I know that it's probably a larger negative value than it should be, if I could somehow show that it actually has a positive bias, that the effect could even be a larger negative value, well, then if I find evidence from my simple linear regression where I know it's biased towards zero, I know that if I had data on this other variable, it might be even further away, right? So I'm at least okay in knowing that I could tell you the sign of that effect. If there was a positive bias, even if I see -50 for that slope coefficient, if the positive bias was 60, the actual effect could be positive, in which case I'm not even identifying the sign correctly. I know the value of that slope coefficient will be wrong, but I don't even have the sign right? So what can we do? So if I run a regression, ignoring this variable x2, I don't include in my regression, I know it's going to create a bias that the slope coefficient I see on this variable that I did include will include the true effect, right? But also this bias component. So if we start to think about what this bias component is, what would beta 2 be? That's the effect of what? So beta 2 is the effect of a 1 unit increase in a second variable x2 on the predicted value of y. So it's telling me something about the relationship between this omitted variable x2 and the y variable I'm trying to predict. What does this represent? So the exam's not going to go off. We don't get used to some of these notations. So we said, what would this be? Hopefully everyone knows this. This is the sigma squared is the variance of that x1 variable. Variances will always be what sign? What's the lowest possible variance I could see? 0. Any other variation, we're squaring those deviations, so it's always positive. So I don't have to worry about the sign of this. What does this represent? It's not the standard deviation, it's the covariance between these two variables. Right? So what I'm really thinking about when I run this simple linear regression without x2, coefficient estimate IC has the true effect, plus we said, put the cam on, thank you. This one's different than the class I teach in earlier in the day and I always forget, so thank you for saying something. So I always know that this is going to be a positive value. This could be positive or negative. What this represents is kind of that relationship between x1 and x2, the variable I included in my regression and the variable I omitted. Beta 2 tells me about the relationship between what? We said it's a 1 unit change in, if I had that second variable in my regression, its impact on the y variable I'm trying to predict. Okay? So if I think through these variables, I often can put a sign, or maybe from other data sets, I have an idea about what the sign of these relationships look like, even if I don't, in my data set, have that information on that second omitted variable. So we'll walk through some examples and we'll see how this can be useful, okay? So, one thing I want to mention, what in this bias equation would help me know that it doesn't matter that I omitted the x2 variable? There's actually technically two things. So when would this go to 0? If the omitted variable has no effect on y, then beta 2 is 0. Anything times 0 is 0. So if it's not related to y, I'm okay. What if it's related to y? What else could help me know that the bias is 0? If it's not related to that x variable I included in my regression. So I only need one of those things to be true to know that there is no bias. If it's ever correlated with y and with that x1 variable I included, now I've got a problem, okay? So if that covariance, or even beta 2 is equal to 0 here, my assumption isn't violated. One of the assumptions we had was simple linear regressions for our coefficients to be accurate, right? To be a true representation of the population coefficient, was that the expected value of our errors given different values for any x variable, right? Was going to have that it has to be not equal to 0. And so in this case, kind of have, if in fact that covariance is something other than 0, that's violated. But if it's equal to 0, now that assumption is met, right? Now, the problem is, are any two variables like truly completely uncorrelated? I mean, there's probably, there are examples, but a lot of the times, even if it's a small correlation, it still exists, right? So more often than not, we have to be worried about this bias, right? And I already kind of mentioned that covariance and the variance. What did we say? If I take the covariance of two variables, this is a weird one, and I divide it by the variance. So if I were to run a regression where I had X1, now what do I want here? Want X2, right? And I'm trying to predict that from my X1 variable. Another thing that we said the slope coefficient is equal to, under, if all of our conditions are met, that slope coefficient, one way we could calculate it, it was the covariance between our X and Y variable divided by the variance that existed. Actually, I want to flip-flop these. Sorry, this is 1 and this should be 2. The variance of our Y variable, right? So really what this looks like is it's a coefficient if we were to run a regression of the variable we included on the variable we omitted. Now, we don't have that data, that doesn't really help us, but just kind of connecting it to some things that we've already talked about. So let's work through this, right? So I've got this bias. I have all these different combinations, right? If the covariance is positive, but the slope coefficient of the omitted variable is negative, well, now I'm going to have a negative or a bias that's kind of pushing my slope coefficient down, right? And then the other 4 combinations, right? We don't need to kind of explicitly state all of them, but there'll be 4 different combinations of these 2 things in terms of if they're positive or negative and what the kind of corresponding bias would be. So let's think through some actual variables with examples, and I think it'll make a little more sense as we talk through this. So let's say I was trying to predict GPA, and now I'm back to a dummy variable regression where I've got athlete is just a 1 if you're a student athlete, 0 if not, okay? So what bias might exist in this coefficient? Okay? So I can think about 1, which is that there might be some selection of what types of students are student athletes versus not. Now, I don't know if it's positive or negative, but if I were to include that SAT score, I'm now eliminating any bias in that slope coefficient on student athlete from SAT score being correlated with being a student athlete and being correlated with GPA. Now, I think, I would argue this might be an easy one. I think hopefully I have it. I don't here, but we can kind of walk through this, right? So if I run that simple linear regression, what would my bias be? Okay. So the simple regression I ran was I was trying to predict GPAs using that student athlete variable. Right. If I exclude this important omitted variable of SAT score, I know that the coefficient I see is going to be equal to whatever the true coefficient is plus that effect if I had included my SAT variable. So I didn't, but if I had included it, what would the effect have been? Okay. And then that multiplied by the correlation of the variable I included, so athlete, and the variable I omitted divided by the variance of, I think it's the variable I included, right? X1. Okay. So if you had to guess, or you got this information from another person, what do you think the correlation between SAT score, if I would hold constant, the correlation between SAT and GPA is? People with higher SAT scores probably tend to have higher GPAs. We can probably put a sign to that pretty easy, right? I know that effect is going to be positive. What's the correlation between SAT scores and being a student athlete? So whether, even if you get rid of all of your negative bias assumptions about, athletes, just being a student athlete means you have less what? Time, which likely means you haven't been putting as much money on average as other students towards studying, things like that. So what would you expect the correlation between SAT scores and being a student athlete to be? Lower. A negative. Or what's probably true about the admission standards for student athletes compared to the rest of you? Lower, right? So this is likely that when I'm looking at student athletes, even at the collegiate level, they likely are going to have lower SATs just from the simple fact that there's additional benefits of the university other than just being a student. They're also an athlete generating lots of money. Okay? So doesn't mean that we're not all valuable as well, but that's the way the university looks at it. So what's the sign of my bias going to be? Well, and I wrote negative here, sorry. This is really what we're talking about is the numerator, right? That covariance negative. We know the variance will always be positive, so we always can kind of ignore that. So what's the sign of my bias? Positive times negative would be negative. I'm going to actually see a slope coefficient estimate from this simple linear regression that is closer to 0, right, than what it might actually be, right? So I might actually be understating the negative impact of being a student athlete in college on your GPA if I exclude this important variable. And the reason why is because once I include it, now it's the interpretation of beta 1. It's the effect of being a student athlete holding constant your SAT score. So now the thought experiment is not just I have one student who's a student athlete, one who's not. What's the difference in their GPA? I have two students with the exact same SAT score, but one of them is a student athlete, one of them is not. Now what's that predicted difference? That's a lot more powerful of a statement. And we can start adding in more and more variables, and then it gets even more powerful, right? Because we're holding even more things constant. But hopefully you can kind of see how we can start to put a sign to that bias, okay? Is that making sense there? More questions on that? Okay. So we just kind of work through that, right? We can actually produce this. So if I run the simple linear regression, I had a data set on this. I think we actually have used this GPA data set. It's pretty large negative value. Being a student athlete decreases GPA by about 0.3 points. We talk about statistical significance. What levels is this statistically significant at? All of them. Now, I've noticed this also in the problem set. When I'm asking about statistical significance, and this will apply on quizzes, exams, on the quizzes and exams, it's usually a little bit more like explicit and kind of reminds you of this. What are our 3 benchmark values? 90, 95, 99% confidence, 10, 5, 1% significance. We need to mention all 3 of them. I understand that it's kind of, if you understand what that means, that yes, if it is statistically significant at the 5% significance level, it automatically has to be statistically significant at the 10% level. But you need to say that. Or if it's statistically significant with 95% confidence, I definitely can say it with 90. But generally, when you're asked about the statistical significance, you need to mention each one of those 3. That lets me know that you understand kind of what this means, okay? Now, is it economically significant? On a rating of 0 to 4.3 seems like a pretty reasonable, like a pretty large change. So we might be concerned about this, right? However, if I include the omitted variable of SAT, what does that coefficient go down to? 0.05. So it is reduced dramatically. We said that it had a huge negative bias in it, right? What was the size of that negative bias? If our naive regression omitting the important variable caused it to be negative 0.28, when we include SAT, we've eliminated that bias. So how much did we eliminate? We went from negative 0.28 to negative 0.05. So that negative bias was about.
I'm sorry. Can the bias be measured in the difference between the R squareds?
And the bias, the actual size of the bias? No, right? And in fact, you could have an R, anytime you add more variables into your regression, what are you automatically going to get? So the R squared tells you how much of the Y variable you can explain, or the proportion you can explain with all your controls. So as I add in more controls, what's the very smallest amount my R squared could go up by? 0, if I add in a completely unrelated control. But even the most, right, even any control I add is probably going to add 0.00001. So my R squared will always be higher. But our bias, depending on the signs, would actually be positive or negative, right? So here, the R squared will be higher. In fact, it's a good thing. I mean, it's a good question, right? So if I look at my R squared, it went up a lot, right? Now, I think what you're getting at is it went up by a lot, right? So what does that tell me? It tells me that the variable I included was just a really strong predictor of my Y variable, right? That I can explain a lot more of the variation in Y because I've included this second variable into my regression. But the actual like size of that bias, all I'm doing is comparing what was my coefficient before to what is my coefficient after. So the bias here was about what? Negative 0.23, if I'm rounding egregiously there. Now, on top of that, not only have we eliminated the bias, it wasn't just the value that was screwed up. What is true now about being a student athlete if I'm predicting GPAs? Is it statistically significant at any of our levels?
No.
Nope. P-value is now 0.26. So it influences not only the size of your coefficient, but also the statistical significance, right? Excuse me. So this is a good example to kind of show that. We can kind of compare and contrast the two. This would tell us the size of the bias here. We don't have any way to predict what that size is without other data sets, right? All we can really do without the data is actually just put a sign to it, okay? So we said it was going to have a negative bias. We knew it was going to be further away from zero, a larger negative value. Sure enough, it was. Okay. Any other questions here? What's something else in this output I could have used to support that if I didn't have the p-value or the test statistic? Let's say I didn't have any of this actually. What could I have used to actually tell you what the new slope coefficient is and whether or not I would reject that at the 95% level? So remember, if we do hypothesis testing with a two-tailed test, which is what we always have here, assuming that it's equal to zero, the slope coefficient, that's also going to be very similar to the outcome we would get from confidence intervals. Confidence intervals tells us these are the possible values for that coefficient. If I've assumed that it's equal to zero, one of the values in my confidence interval, can I reject that? This represents the possible true values. So if zero is in this range, could I reject zero? No. Well, sure enough, I failed to reject that p-value. Whereas with this other variable, is zero in my range? No. So I should be able to reject that. Sure enough, if I look at that p-value, it's going to be less than 0.05, right? Because I only have the 95% confidence interval. And then what if I wanted to tell you what's the size of that coefficient just using my confidence interval? How could I do that? What was I building my confidence interval around? I was going a certain number of standard deviations to the above to get my upper bound, same number of standard deviations below to get my lower bound. So where will my slope coefficient be? Exactly in the middle of that confidence interval. So how would I find the middle of this confidence interval? Average. Average, so just add these numbers up and divide by 2. So kind of connecting these hypothesis test results with our confidence intervals, they really are telling us the same thing. Is that clear what I'm getting at there? Any questions on that? So we already mentioned these things. Oh, is there anything else I want to say? Oh, so I'll try to just kind of prove this to you. If I had the covariance, so I actually had the data on SAT, so I can prove that what I told you to calculate the bias is in fact what it should be. Remember, my bias was, what would that coefficient have been if I did include? Well, I showed you the regression results, so we had that. It was like what, 0.001, whatever that coefficient on SAT score was. Now all I need is the variance of athlete and the covariance of athlete was with SAT. So I ran this covariance matrix. So I did this correlate command and then said, give me the covariances. This is something that we looked at already. So what's the covariance between student athlete and SAT score? Right here. What's the variance of the athlete variable? Well, variance is essentially the covariance of something with itself. So that would be right here. The diagonals were our variances. So I now have the variance of the variable I included, athlete, the covariance of what I included, athlete, with what I excluded, SAT. And because I had the actual data, I now know my coefficient on that SAT variable if I did include it. If I take those three things and I plug it into that bias equation, hopefully I come up with what value? So we said the size of the bias was what? We went from negative 2.8 to negative 0.05. Hopefully I get negative 0.23 unless I'm lying to you. Right? So if I go ahead, plug in that coefficient, plug in the covariance, plug in that variance, sure enough, I get the size of that bias was 0.23, not even 0.23, it's negative 0.23. Questions on that? In fact, I think I changed the size here. So let's do that so we can actually see everything. There we go. Yeah.
So can I argue something as economically significant regardless what the p-value is?
Yeah, we don't really focus on it as much in this class because really you could argue there's always going to be a threshold, right? If I tell you that an effect on GPA of 0.2 is large, you could tell me that, no, I only think something above 0.25 is large enough, right? Like, and you have to have some support behind why you would think it's economically significant. But generally, I mean, I would think about if I'm trying to predict something, it kind of depends as well. Like, even if I find it, like if I'm an admissions department and I find a difference in the GPA, like of 0.1, 0.2, what can that make the difference between? Well, Kelly, I think just got like ranked #1 or something, like for some poll or for some thing on business schools. What do you think is probably true about the GPAs of those schools in the top 10 average? They're very close.
Mhm.
So for them, what's economically significant? I don't know, maybe 0.0001, right? Like if it's gonna push me, so it kind of, economic significance is always very dependent on what question you're asking and like what the stakes are, right? But I like to mention it along the way so that we can start to think about, just because we have a statistically significant result doesn't always necessarily mean like we're gonna put an increased amount of focus on it, right? And there I would even argue they probably don't care if it's 0.0001, like, because they're looking for things that have even larger effects,
Mhm.
right? Does that answer your question?
Will it be tested on like a?
No. I won't ask you like our economic significance is kind of arbitrary.
Got it.
I'm just trying to give you things that when you go out there and actually work with data sets and you're working for companies, like, or it doesn't have to be companies, it could be nonprofits, school organizations, like we don't want to get too lost in the weeds of statistical significance and remember, like, does this have an actual economic significance on the variable we're looking at?
Gotcha.
Does that make sense?
Mhm.
Excuse me. All right. So, kind of returning to multiple linear regression, I kind of already mentioned this because I had a question along the way, but we said as I added more X variables, right? If I use more of these independent X variables, what's the very worst the R squared do? Stay the same. So we know that as we add in more of these variables to our regression, our R squared should go up, right? Now, how much it goes up does signify to us, was this an important variable to add to our regression? If the R squared goes from what we had before, was like what? 0.008 to 0.16, how much more of the variation in GPAs did SATs explain? Almost 15%. Well, explaining 15% of a variable with just one other variable, that's a pretty big increase, right? There's likely a lot of other things that matter that impact the student's GPA, and we found something that it can account for 16 of 100% of the variation. That's pretty, or I said 16, 15, right? Depending on how we round. So R squared should always increase. And we kind of already looked at this. I forgot I reposted these regression results, right? It went from a very small value to very high. That's because probably your SAT score is going to be a lot better predictor of someone's GPA than just if they were a student athlete or not. So we want to start kind of looking at these R squareds across these regressions as well. Now we mentioned this last class, which was the idea that even with simple linear regression, I said, as we have higher sample sizes, we want to kind of penalize ourselves for just getting more and more data to find the same result. So we had our R squared, which was like how much variation we're explaining over the total variation. That's all our sum of squares. We said another way of writing this is just 1 minus the proportion that I can't explain. So RSS was the residual sum of squares that I can't explain. We then said, we'll take this version of R squared and we're going to adjust that proportion we can't explain by this fraction. Now, when we had the sample size, we said as the sample size goes up, what's going to happen to this fraction? So we can think about this with really low numbers and sometimes it makes sense. So K was the number of variables we included in our regression on the right-hand side. So let's just assume for right now that was. If I had a sample size of 3, what would this fraction be? 3 minus 1 is 2. 3 minus 2 would be 1. 2 over 1 is 2. So this is going to get multiplied by 2. So I'm going to be subtracting a large value. Now, if my sample size is 10, what's this fraction? 9 over 8. That's a lot closer to what? 1. In fact, as my sample size goes up, we said this is going to get closer to 1. So my adjusted R squared is going to get closer and closer to, if I multiply this by 1, I just have my R squared. So higher sample sizes will actually, are going to increase our adjusted R squared, and it's gonna get closer to that actual R squared. Instead, vice versa, if I have lower sample sizes, my adjusted R squared is gonna be even further away from my R squared. So let's think about what this will look like, K, because we now have a new thing in there, right? So my R squared was 1 minus the proportion I can't explain. So this was my adjusted R squared. I'm going to take that same proportion I can't explain, but I'm adjusting it by this factor. Okay. So let's assume we have the same sample size, same data set, but I start to increase the number of variables I'm putting on the right-hand side. So I'm including more variables to explain why. Okay. Just before we even walk through it intuitively, if I'm using more variables to predict something, are my predictions going to be more or less accurate? More accurate, which means, do we need to really penalize our R squared as much? No. So what should happen is I add more variables to that gap between my R squared and adjusted R squared. Should be going down. Sure enough, if I increase the number of variables, what's happening to this fraction? Denominator would actually be, I'm subtracting a larger value in the denominator. So this denominator is going to go down. What happens then to this fraction if my denominator is smaller? This goes up if I'm subtracting a larger value here, right? What's going to happen to my adjusted R squared? Yeah. Wait, what did I just say? It's counterintuitive, right? So with a sample size, it kind of is intuitive in that when we have more of these observations, our R squared and adjusted R squared, we have more data, we shouldn't be penalizing ourselves as much. What we're going to do here is we say, well, guess what? I know that if I throw a couple hundred variables on the right-hand side, even if they're not that related, I can always get better predictions. So what we're actually going to do with the adjusted R squared is we're going to penalize ourselves for just simply adding more variables, right? So it actually is kind of counterintuitive. As I add more variables, what am I actually doing? I want to penalize people for just throwing in variables that are kind of like throwing stuff at the wall, just kind of guessing, right? So as I include more variables in my regression, my adjusted R squared, I'm actually going to get penalized even more. So the gap between my R squared and adjusted R squared actually gets further or larger as I add in more of these independent variables. So I kind of started out, so I give you, this is a counterintuitive result, I think, on its face, right? But it kind of, once we start to think about, oh yeah, it kind of makes sense. I know I can always increase my R squared by just adding more variables. So I want to penalize people for just throwing, like, you'll see some of these regressions, like when they're trying to predict stock, like they just throw everything they can possibly think of in there. Well, that's always going to increase my R squared, but I might just be adding more variables that potentially would be correlated with other omitted variables that actually even make my results worse. So we're going to kind of penalize ourselves more for just adding more variables in there. Okay. Any questions? And you can always, with this, and we'll have a formula sheet. I'll put that up when I put the practice kind of exam questions up there. And you can always kind of use this arrow to think through, like, okay, you have to know what K represents. But as you can use these arrows, once I know, okay, I'm putting more variables in there, decreases my denominator, increases this fraction, subtracting a larger value, that'll decrease my adjusted R squared. Okay. Any questions on this idea? Okay. All right. So we kind of talked through this. Let's say I have this regression, right? And I've got EPA, I've now included both of these variables, right? My adjusted R squared will always be lower than my R squared. But why are these so close together? Two reasons. I think I mentioned one specifically in the slide, which is what I was using, but there's really two. What's my K here? It's the number of independent right-hand side variables I've used. 2. So I'm not getting penalized very strongly for that. So the gap isn't going to grow much between that R squared and adjusted R squared because of that. What's going to cause the gap from the adjusted and the actual R squared to get closer? I'm including 4,000 observations. So that fraction is going to be really close to 1, which is gonna make that adjusted R squared essentially the same as my R squared. In fact, you know, if I'm rounding these to the 3rd decimal, I wouldn't even be able to see the difference. So we'll start thinking about dummy variables here. What do I want to do? So we've got 35 minutes. I think we got enough time to start to do this before we switch here. So we talked about dummy variables before. So I had like a wage thing. When we kind of think about if I were to run this regression where I'm interested in the effect of IQ on wages, right? And maybe I want to control for, I here have like a racial identifier for someone, right? Well, what could cause kind of this relationship to vary is potentially maybe people of a certain race are treated differently, right? And so maybe this relationship or the relationship might be the same, but the starting point, if you're treated differently by employers, might not be, right? So if I think about kind of graphing this out, if I had this regression and I'm looking at wages and I had IQ, and I included this dummy variable for whether or not the individual was identified as Black, right? There's just a 1 if they were, 0 if not, okay? So I'm gonna throw this up here just so I can reference these values. If I was to plot this, and I'm thinking about, okay, what's the impact of my X variable, IQ, on wages? For someone who is not identified as Black here, where would the intercept be? So where would the predicted value be when IQ is 0? What's the intercept for someone who's not identified as Black? Well, 0 times anything is 0. 0 times anything is 0. So their starting point might be right here. And then as IQ increases by 1 unit, how much are wages increasing by? Whatever that slope coefficient is, and technically I should have said this is our estimate, right? That was coming from some regression. So I'm guessing that it's positive, hopefully, right? As you're more intelligent, you expect to see a higher wage, right? Now, if I think about for the second group, where would their intercept start? Well, when IQ is 0, 0 times anything is 0, so that would go away. So theirs would start at what? Beta 0, but then also, if that individual is identified as Black or whatever dummy variable group we have, they would get added in this coefficient, right? If for whatever reason this group is negatively kind of impacted by employers or whatever the example we're looking at is, if I assume that beta 2 is 0, where would I plot that intercept? Beta 0 plus beta 2 would then be down here. So what I'm doing with dummy variables, it still has the slope here be the same, but I'm identifying differences in the starting point for my different groups that this dummy variable is identifying. So having a higher IQ is going to lead to a higher wage for both groups here. They're going to start out at different points. So it's almost like when we run these regressions, when we include dummy variables, we're actually getting like multiple lines of best fit. So like I might have a scatter plot of data. If I looked at all the people that belong to the 1 group here and all the people that belong to my 0 group, I'm coming up with the same kind of slope based off of those scatter plots, but I'm really almost like, in a way, estimating 2 lines of best fit, right? 1 for the 0 group, 1 for the 1 group. Does that make sense? Any questions on what I'm kind of getting at there with that graph? Okay. So all right. I left that open to kind of draw that for us. This is a throwaway slide because basically the way we've already done this today, but statistical significance when it comes to multiple linear regression, no different than with simple linear regression. We're doing the same test. We can do other types of tests, but we're always going to do this test where we assume that that slope coefficient on that variable is equal to 0. So always a two-tailed test. Benchmark value is always the same. Comparing the p-value to alpha, nothing really changes. We just can do it for every variable in our regression. Right? So here, kind of some of our assumptions that we have. So this assumption we were worried about that was being violated when we omitted an important variable, if we've included these important omitted variables, we now have this is met again, right? That now conditional on all the other variables we've included in our regression, now for different values of this X1 variable, our expected error is equal to 0, right? And hopefully if we've included every single important variable in our regression, that assumption should now be met again, right? We shouldn't be missing anything. We're not omitting anything that's important. This one, we won't focus too much on, but basically every variable should have an independent distribution. And then we don't have extremely large outliers. I said, what are some types of variables that could be an issue with? Income, right? Where we have really, really high values. If we're looking at companies, maybe one company in our data set has like an astronomically much larger revenues than others. But we won't really dive into these issues a lot in this class. These are just some of our assumptions. The one that we are going to now focus on that we didn't really have with our simple linear regression is the idea of what we call multi-collinearity. So once we start adding in several variables, multi-collinearity means if we have two variables where they're exact linear functions of each other. So this would be, let's say I had, if all these are met, we say this is blue. So I want to kind of go to thinking about, let's say that fourth assumption with multi-collinearity, how might that be violated from like a multiple linear regression? So let's say I had a variable and I identified if you were we'll do the GPA, college, and I identified if you were a freshman, had a dummy variable, 1 if you were, 0 if not. Sophomore, new variable, 1 if you are, 0 not. Junior, 1, 0, senior. If I include all of those into my regression, anytime freshman is 1, what do I know sophomore, junior, and senior are? 0. Is there any base group? Who am I comparing to? If those are the only 4 classifications, now my coefficient on freshman would be if I'm a freshman, I belong to the 1 group relative to the 0 group, but who's the 0 group? There isn't one, right? Those 4 dummy variables would be exact linear functions of each other. As soon as I know one, automatically know the value of the other 3, right? And so I can't include a dummy variable for every single group. I need to leave one of those groups out. Okay? So here I've kind of got this example. This is really even more basic than what I just went through. If I include the same variable twice, anytime I hit here, if I have a traffic stop data set. So I think a ticket was just, you got pulled over, 1 if you got a ticket, 0 if not. If I included whether the driver was male as my predictor variable, if I include it twice, every time driver male is equal to 1, what would driver being male equal to that second variable? It's always coded the same thing. This is perfect multicollinearity. These 2 variables, right? It's the same variable, so I know it's violated. So what does Stata do? Luckily for us, we want to understand the idea that we can't do this, but luckily for us, Stata can identify perfect multicollinearity. What did it do? Toss it out. So if you make a mistake and you accidentally type the same variable in there twice, it'll knock it off. They'll throw one of them out for you.
It won't detect it though. It's not perfect, right? Like if
It's not perfect multicollinear. So this would be, we won't really dive into these issues probably even today. If I had something like, usually these are going to be examples where you're thinking about like a time in a day. So if I work more hours, what inherently do I know I'm not going to have as many hours to do? Sleep, study, right there. Direct functions up like they are direct linear functions of each other, but it's not these easy examples where they're just dummy variables, right? But I know they're direct linear functions because there's only 24 hours in a day, right? So the imperfect multicollinearity gets harder to think about, and probably not going to ask you as many questions. I'm not going to dive into those issues as much. I know I've got some things here where we'll mention it probably on Thursday. But for now, we're just thinking about perfect. But yes, Stata won't identify those. So what if I have multiple dummy variables? This was like the example I gave you with freshman, sophomore, junior, senior. I said, really the solution is you got to leave one group out. They're going to be your comparison group. So if I had my example of freshman, sophomore, junior, senior, who, if I'm trying to predict, like, I don't know, belonging in one of these, what's the impact on your GPA? I mean, who would you probably choose to leave out? Either what group you think probably is going to have the lowest GPA, or you might want to leave out who you think has the highest. Because now your coefficients will always be relative to that group. it's gonna look a little bit cleaner in the data. So I'll give you an example. Maybe we can think about what I'm getting at here. So let's say I had, instead of the sophomore, freshman, junior example, let's say I'm trying to predict wages and I have different dummy variables for degree types. 1 zeros, high school, some college, college degree, graduate, or professional. And let's just say I don't have any less than high school here, just for the sake of this example, right? Which one of these would make the most sense to probably leave out? So what am I really trying to get at if I use these dummy variables to try to predict wages? The effect of education on wages. So if I had the coefficient on some college, what do I probably want to reference as the zero group? So this would be the effect of having some college, the predicted change in wages relative to whatever group I leave out. So the group I'd want to leave out is probably the lowest education level, right? If I left out high school degree, what would I expect the coefficient sign to be for these other three dummy variables? Positive. Now I could also do this the other way. What if I left out graduate or professional degree? Now what would I expect the sign on my three lower dummy variable degrees to be? Well, I expect this is probably the group that has the highest wages. So now all these coefficients, if I include these three instead and leave out this group, now all my coefficients would be negative. So it's really a matter of preference, kind of which one you leave out. You still get the same information, but it's just displayed a little bit more cleanly, right? If I want to tell this story about how education is impacting wages, right? So if it's ordinal, choose the lowest or highest category, makes the most sense. If you have no idea, just choose one, right? So I had an example here where I had some revenue data and I was going to try to predict these different conferences in college. I think this was, I don't remember if this was football or basketball data. It doesn't matter, but it was the athletic department's revenue and what conference they belong to. Well, I need to leave out one conference. Without looking at the data, I didn't have any clue what the lowest. I probably could have guessed from a set of 5 or 6, but I didn't know which one exactly was the lowest. Now, what could I do if I had the data? Simply calculate the mean for each group and figure out what the lowest group was, then run my regression. But I could just choose one. So I think I chose what, I don't even know, the AAC is the American Athletic Conference. I don't even know where the hell that's at. But that's the one I left out, right? So now when I look at my regression results, actually here, it identified, well, it's not going to leave out the AAC for me. It leaves out the independent group. So that's the one that Stata chose to kick out. Because I included a dummy variable for every single possible conference, it kicked out one of them. Now it usually defaults to the one that has the lowest number of observations. Not that I'm going to quiz you or expect you to know that, but that's why it omitted this independent group. So if I looked at these coefficient results, kind of hard to look at because what does that e to the positive 7 mean? Move the decimal 7 places to the right. So these are very large values, right? These are large revenues, right? And basically, without any other regressions, what would these actually tell me? So what would the constant tell me? If I'm trying to predict wages, the point where it starts out will be when every x variable is equal to what? 0. So every variable here I include in my regression is equal to 0. I'm actually looking at what the average revenue would be for that group that was left out, those are independent colleges. If I then want to look at, okay, what is the expected revenue for the Pac-12? It would be the constant plus this coefficient. So these kind of tell me like where the starting point would be at or where the average revenue would be at for each one of these conferences. So what conference here would have the lowest predicted revenue? The one whose coefficient is. So if I'm predicting total revenue, all I have are these dummy variables.
Sunbelt, right?
So all I would do is when I'm making the prediction for different conferences, it would just be that constant plus the coefficient. So what am I looking for? I'm looking for what coefficient is the largest negative value. Negative 1.82 looks like, yep, that's the largest negative value. So that's going to be the conference that has the lowest revenues. What conference would have the highest total revenues here? Conference with the highest coefficient, right? Because all I'm doing is taking the constant, adding in that conference's slope coefficient. So whichever one has the highest slope coefficient, whichever dummy variable that is, which looks like here, it's the SEC, right? That's gonna be the conference with the highest. And then I could rate them just based off of the size of their slope coefficients. Now, if I did leave out the AAC, what's gonna happen? For example, oh, do I have a good one? This might be. Oh, that won't work. Might be mine. Let's say I left out the SEC. What's gonna happen to every coefficient for every dummy variable in this regression? If I leave out SEC, we just said they're the conference that would have the highest predicted revenues. So now my zero group that I'm comparing to is the SEC. So now every slope coefficient will tell me that conference's change in predicted total revenues relative to the highest group. So now all of my coefficients should be negative. If I left out the lowest group, Sunbelt, now all my coefficients would be positive, right? So we can kind of just thinking through these things to kind of, think harder about what we're doing here. We've kind of already talked about this question. I'm kind of jumping the gun a little bit. So, where are we at in time? We got 20 minutes left. So what do I want to go through here? That save us enough time? I think so. I think we got enough time to get through this, and then I'll kind of go through some sample questions with you. So I had this other example I was thinking about where I had that traffic stop data, and I was thinking about like trying to answer questions that seem a little bit more interesting than like college athletic revenues, which is like, are people of different races treated differently by officers of different race? Right. So is there like, if I'm get pulled over and I'm black, is a white officer more likely to write me a ticket? That seems like a question we might want to know the answer to, right? Hopefully that effect is zero. Hopefully we can fail to reject the null in that case, right? So what I did was I said, okay, look, I can include these dummy variables kind of like I did in the previous example, but I can also start to include additional controls. So here I've got like the driver's age. I didn't have a lot of data in this traffic data set, but I can control for the driver's age. If I had to guess, what do you think the sign of driver's age, right? If my Y variable is whether or not I was issued a ticket, so this is where we want to start to think about dummy variables as our Y or our X. What's the units of my Y variable? If it's a 1 or a 0, if I got a ticket or not? So that coefficients would be changes in the
Proportion.
not percentage, but probability or proportion that I was given a ticket. We wouldn't really say proportion, but you're thinking about it the right way. So what do you think the sign of beta 1 probably is? If we forced it to be linear, my guess is the longer you drive, the less likely, hopefully, you're getting. I should have gotten a lot more tickets than I did when I was 16, right? So I'm guessing that it's probably a negative correlation, right? As I get older, I'm less likely to get a ticket when I'm pulled over. I'm also probably more likely to treat the officer with a little more respect than when I was 17 or 18, okay? Now, I also had in the same data set whether or not you were arrested at this traffic stop. So I'm looking here at like low levels of discrimination and whether or not someone was issued a ticket, and then high levels of discrimination, whether or not they were arrested. And I was looking at these different combinations of was the officer black or white and was the driver black, right? So what I did was I threw a bunch of things at this, right? So I said, okay, if I can control for the officer's race, I also have controls for what the driver's race was, officer's years of service, whether or not I had gender of the officer. These, I don't remember which one's which, but these are really important. Like if I just ran this regression with just these like demographics, what could you argue? I don't know, that may be different depending on what city this is in or what region of the country. Maybe different groups demographically might be correlated with being pulled over for different reasons, right? Now, if you look at the data, that's not necessarily true, but to circumvent that issue, what I can do is say, I have all these identifiers for the reason of the stop that the officers have to register. So if I can control for this, I'm controlling for the reason why the person was pulled over. So now if I look at this coefficient on whether or not the driver was black, right? I'm saying holding constant the officer's race, officer's gender, and the reason for the stop. So the thought experiment has two people pulled over. Officer had the same years of service. Officer was the same gender, same race, but same reason for the stop, but one of them was black. What's the change in the probability they were issued a ticket? That's a lot more powerful of a statement. I have them controlling for a lot of other things. So good news is, what did I find here? The probability you're issued a ticket, if you're black here, actually goes down. Now, goes down by 0.008. And is it statistically significant? At the 90-95% level, because our p-value is less than 0.1 and 0.05, but I couldn't say this with 99% confidence. And also, my p-value, I still can't say it with 99% confidence. What made it that I should hopefully be able, if there really is a strong effect, I should be able to reject at any level? What's going to make it more likely I can reject in this regression? We have a really high sample size, right? So that should automatically make our p-values pretty low. Sure enough, most of these p-values are 0, right? So it is statistically significant, but we needed a lot of data to do this. So good news, doesn't look like it's still, I can reject here that slope coefficient is equal to 0, like it's slightly negative. It actually looks like maybe there's not discrimination going on here. Right? And even the size is relatively small. Now, the not so good result is, so we're kind of looking here, we already mentioned this, it's pretty statistically significant, even a little bit less likely to be issued a ticket if I zoom in on these results, okay? And then I kind of had the group that's actually being discriminated against here in a positive direction was actually Asian drivers, right? By quite a bit, like 0.04, that's like a 0.05 increase in the probability. That's a 5% increase. And that's holding constant all those other factors. So that's not, that's pretty decent evidence of some discrimination going on. Now, if I look at whether or not they were arrested, here's where it gets a little more interesting, right? So if I zoom in on the results here, so I ran this regression, everything's the same, but my Y variable is now not whether or not I was issued a ticket, it's whether or not I was arrested. Now, holding constant the reason for the stop. And like one of these reasons was like, there was a warrant out for your arrest. So we're holding that constant. So we're saying two individuals, even if they were pulled over for both having a warrant out, what's the change in the probability from simply the fact that they were identified as a different racial group, right? Now, when we look at these results, what's that coefficient on whether or not you're black? The change in the probability you're arrested goes up by 1%, which, might not seem like the largest, but I don't know, getting arrested, if you told me the probability was going up by 1%, I'd be pretty concerned about that, right? Even though it's a relatively small size, like I don't want to get arrested. So here, not only do we find that this group is being treated differently, we can say that at every statistically, I can say it with 99.99% confidence, right?
See, the other variables also at that 0.01 level, is that like is that like white?
Which one?
Is black, Hispanic, Asian, other?
Other was like, I think if I remember right from the data set, it was like they had multiple rate, like it was based off of their driving records or something. So like if they selected several racial groups for them, like they identified with several racial groups, they were treated in the other category.
Okay.
So the group that I left out here, if I'm trying to identify discrimination, what group do you think I left out and you don't see up here? White, right? So all of these are relative to a white driver. Right? Now I could have left out any racial group, but that my imagination was that I expect the discrimination is going against non-white drivers. So I left out the group of white drivers. If I had included white as a dummy variable here, what problem would I run into?
I'll take, you called it.
Perfect multicollinearity, right? And that's mainly because I had this other category. So I know I have every single race. I have to leave one out. I left out the white category. If I had included it, Stata would have kicked out one of them. I don't know which one. I think probably other because it probably had the smallest number of observations. But I can choose which group I want to leave out by simply leaving it out. Any other questions on this before we keep moving here? So I don't know. I put kind of the summary of some of these. We might be concerned about omitted variables. Data set, didn't have everything. So these results, take them with a grain of salt. There's likely a lot of other things like maybe previous arrest, previous traffic tickets, there's a lot of other information that we would likely have omitted, so there's probably some bias in these results. But these are the types of questions we can start to answer, right? And hopefully, I don't know, you're finding this like kind of interesting, right? We can identify some pretty important things. So we didn't really do any work in kind of Stata here today. I might have a little something I'll show you at the end. If not, we'll kind of start with it on Thursday. But I mean, I say we didn't do any work in Stata. Hopefully, I mean, we know how to run regressions, and so I'm kind of showing you a lot of this regression output. Kind of for up until the next exam, a lot of what we're going to be looking at is probably less like work in Stata and more of interpreting the results, right? Of multiple linear regression results. So what I do have that I want to look at today is this 4th class quiz. So go here. I've got a couple questions. Oh, and I'm gonna change this real quick. Wasn't sure where we had. I just set this placeholder. We'll make sure it's the end of class. I will take a look at it. In class quiz 4. Without. And I'll kind of walk through questions and help you answer them, right? So let's hold off on one since we kind of covered this at the beginning of class. We'll kind of return to it, right? So let's say I was looking at this regression where I'm running the number of sessions. So I have these, I teach the 251 that, and I think you guys take 250, or I forget the exact number, but it's a huge section. I have these additional help sessions. And I actually had the data where I ran the regression of the number of sessions a student attended on their exam score, right? So which of the following variables would I think are more likely to have perfect multicollinearity? Okay. So if I'm thinking about perfect multicollinearity, right, I need something that's a direct linear function of this number of help sessions attended. So if I'm thinking about their quiz scores, I mean, it might be correlated with that number of sessions, but is it going to be a direct linear function? Just because I attend one more session, that's not going to automatically give me a higher or lower quiz score. So that one shouldn't be perfectly multicollinear. What about their IQ score? Same kind of idea. These need to be direct linear functions where if you tell me the number of sessions they attended, I can almost 100%, in fact, if it's perfect, I can 100% accurately predict what this other variable is. That would be the case for IQ. Attended additional tutoring sessions. Once again, I don't know. I can't tell you the exact number. Classes attended, right? Oh, sorry, class attended. This additional tutoring session, this is a dummy variable if they simply attended one of these sessions. So let's think about that. If I have these tutoring sessions and in my regression, I just have the number. So it could be 1, 2, 3, 4, 5. I think there was 12 throughout the semester. But I have a dummy variable that's a 1 if you attended any, 0 if not. If I know the number of sessions you attended, would I automatically know what this dummy variable is equal to? Well, if you attended one session, what would this be equal to? Did you attend at least one? Yes. What if I attended 2 sessions? Be 1. What if I attended 3? What if I attended 0? This would be 0. So if you tell me the number of sessions, I can tell you the value of this dummy variable, which means they are perfectly multicollinear. If I know the value of one of these variables, right, I automatically know the value of the second. Right? And it doesn't have to work both ways, right? If you told me this was 1, I don't know that the number of sessions is 2, 3, 4, 5. So it only has to kind of work in at least one direction for them to be perfectly multicollinear. Okay? So we want to be careful when we create our own dummy variables. So for example, if I ran this regression and had IQ, and then I had a dummy variable was IQ above or below the mean. As soon as I know IQ is above a certain value, I automatically know that dummy variable is going to be equal to 1. I can't include both of those, right? So if I'm ever creating a variable from another variable like this, like creating these dummy variables using another variable, it's likely I'm going to have perfect multicollinearity, right? So this is going to be the one that we would have perfect multicollinearity. So I think here I'm asking you for which of the following would lead to, so the only one there would be if they attended kind of one tutor, that variable is the one that has perfect multilinearity. Okay. Now, what if we had this second one? So I use a little trick here, and we'll look at this in Stata next class, but I can include several dummy variables without like adding one for each one. So I have like this way of doing it in Stata using this IDOT command. So we'll kind of get at this next class, where it automatically creates a bunch of dummy variables just for my regression, and it doesn't add them to my data set. Talk more about that next class. But all we care about is I can run this regression where I'm looking at the total value of a player's contract based off of, this must be football data, what position they play. Okay. So if I'm looking at this and I said, okay, what is the difference? So if I'm looking at the omitted variable, which is center, what's the difference between a running back's predicted salary compared to a wide receiver? Well, all of these coefficients will be relative to the group that I left out. So all of these will be relative to that center position. But if I want to know the difference between what I said, running back and wide receiver here, well, if I made the prediction for my running back, it would be my constant plus this value. Wide receiver would be my constant plus this value. So if I want to know the difference in the prediction, it would simply be what? Well, they both include the constant. So the only difference in the predicted total value of their contracts would be the difference in these coefficients. So if I look at like kind of what this difference is, it looks like it's going to be what? Relatively looking right around 2 million. I'm looking at this, right? Running backs earn about 2 million less. So I think it should be this value right here, right? I don't know, what is this? 1.3 versus 3.3 million. So we're right around that $2 million value. Okay. So, and that's just comparing the difference between the running back and the wide receiver. Okay. That makes, what if I wanted to know the difference between, oh, I don't know, the defensive lineman and offensive lineman? What would I do there? Simply look at the difference between their coefficients, right? So just because I leave one group out, I can always compare whatever two groups I'm interested in by simply looking at the difference in their coefficients. And then if we had the same kind of thing, but I wanted the difference between a punter and a kicker, what's one regression I could use where I don't have to use two statistics? I don't have to look at the difference in the coefficient. What's one way I could do this? Okay. So if I have all the different positions and I want to know the difference between punter and kicker, which one of these would give me just one slope coefficient that tells me that difference? If I left out, the group I leave out is always my comparison group. So up here, this was always the change in the predicted total value. I think it was over their whole career from an offensive lineman relative to a center. So if I want to know the difference between a punter and a kicker, I would want to leave out
Or the kicker.
either the punter or the kicker. Now, whichever one I included, that coefficient will be relative to who I left out. So I could either leave out the kicker variable only or leave out the punter variable. I don't want to leave them both out at the same time, but I only want to leave out one of these groups, right? To avoid perfect multilinearity. But if I just want to look at one slope coefficient that would tell me the difference between two specific groups, I need to leave one of them out. Right? So in this case, it would be both of these, right? I'm looking for all that apply, so it would be both of these. Okay. Any other questions on those three? Okay, so we've got one more here. Let's just save a little bit more time here. But if I'm running this regression back to that kind of exam score example, and I leave out the important omitted variable of internal drive, right? So let's say I have your exam score, and I try to predict this using the number of sessions. My coefficient that I see will include the true effect plus what? The coefficient on the variable. Sorry, quickly not thinking. If I had included, if I could have some measure of the internal drive of my students, right? And then times the covariance of the variable I included with that important omitted variable of internal drive. And then we had over the variance of that variable I included, right? So what do you think the sign, if I did include internal drive, this is gonna drive me to study more, et cetera. What do you think the impact is gonna be on my exam scores? Beta 2 is likely positive. What do you think the correlation is between internal drive and the number of these additional help sessions that they attended? Probably also positive. So my bias is going to be positive. The result I see from my simple linear regression is always going to be higher than what it should be, or it's going to have this positive bias built in. Okay. So did I make it on time? I think it was set to be 3:35 here. In fact, I'm going to do something here. If you guys don't mind on the way out, just so I can verify who was here. If you don't mind writing your name down right here. That way, if you got it submitted and it was a little bit late, verify that you were here. We talked through all of them, so everyone should kind of just get full credit. So if you want to write it down your way out, I'll give everybody credit for simply being here today for this in-class quiz. So start working if you haven't, sure, on that problem set 2. Tomorrow, my office hours are going to be very busy because I just gave an exam to my 251 students. So if you have questions, you can stop by, but it's going to be first come, first serve. It might be a little bit of a line. If there's other times that work for you, either tomorrow or Friday, feel free to send me an email. But that I'll change the due date and that to be the end of the day Friday because of a little kind of static hiccup. Okay. Other than that, I will see you guys on Tuesday. See you guys on Thursday.
Thank you.
I just had one quick question.